Hey everyone, so I'm in the Khan Academy class for statistics and probability. Today I'm going to be going down to the unit 10. I'm going to do the unit test for unit 10. The unit is on sampling distributions. So we're going to head to the bottom. So the unit test. So what I'm going to do, I'm going to use two equations basically. So I think I'll probably just kind of go ahead and write those now. So let me write it over here. So we're talking about sampling distributions. So it's the idea that when you take a sample, you don't always get the answer that you think you're going to get. And it turns out that the way that the answers will start to form if you start taking more and more and more samples is into a bell curve or a normal distribution. So if you take a bunch of samples, you're not always going to get the exact answer, which is probably right here, right? It's probably right in the middle. Like that's probably whatever the exact answer is, whatever you're trying to get is like right there. But sometimes you'll get something lower, sometimes you get something higher. But the answers that you get will start to like peak in a bell curve right where they should be, as long as you're taking big enough samples, random samples, as long as you're taking proper samples. What we're going to do is if we're measuring percentages, in the question, it's going to say proportions, but I'll think of it as percentages. A percent is a proportion, so I'll write that, proportion. Proportion. So if we're taking a sample and we're measuring a proportion, that means we're measuring a percent of something. Like what percent of people are over 6 feet tall? What percent of iPhones cost over $500? I don't know. It's probably a lot of them. So if you're measuring a percentage, the samples that you take will start to center around whatever the true percent is. So the center of your sampling distribution will be the true population percentage. So I'll say the mean of the sampling distribution will be equal to whatever the true population percentage is, which is in some percent. And the standard deviation of these results will get smaller as the sample size increases. If you take bigger and bigger samples, the distribution of these samples will get tighter and tighter and tighter because you're going to more reliably get samples that are close to the mean. So it's going to decrease the standard deviation. We call this the standard error. It's the standard deviation of the sampling distribution. And the way you calculate it for percentages is it's the square root of whatever the true percentage is that we think that we're looking for. It's going to tell us that in the question, times 1 minus that same percentage. So these numbers will always add up to 1. And then the denominator is going to be n, the sample size. So whenever we take samples, we're not always going to get the answer we want. They're going to follow a bell curve. The center of the bell curve will be the true answer, which is p, the true proportion, and the standard deviation of our samples will be the square root of p times 1 minus p divided by n, where n is the sample size. Sample size. So the only other formula we're going to need is if we do end up having, instead of measuring a percentage, if we're measuring an average. So if we're measuring like what's the average height or the average weights, what's the average shoe size, the middle number, it's still going to be whatever the true population average is. But in this case, it's not a percent, it's a number. So maybe you're taking the average weight of elephants, and maybe that's something in kilograms. Gosh, I don't know. I'm going to guess 1,000 kilograms. I have no idea. But let's say, for example, of all these elephants, on average, they weigh 1,000 kilograms, but the standard deviation of all the elephant weights is, let's say, 200. So the average weight of elephants is 200, but the average weight of elephants is 1,000, and the standard deviation is 200 in kilograms. So what's going to happen is if we take samples of elephants, these samples will also start to follow a bell curve. The samples should center at 1,000. And depending on the sample size, the distribution will be tighter. If a bigger sample size will give us a tighter distribution. So the standard deviation of this sampling distribution, it's again called the standard error. The way we're going to do it is it's going to be the standard deviation of within the population, which we know is 200, but we're going to divide that by the square root of the sample size, n. So it's the same n from the other formula. The only difference here with the blue is that we're measuring averages. We're measuring like an average weight. Versus a percent. So the formulas just are a little different, but we use the standard deviation of the population divided by square root of sample size. So 200 would be the numerator, and then as the sample size increases, the deviation from sample to sample would decrease. Okay, so let's get started. All right, so I'm gonna get my mouse here. Let's go. All right, so this question says, shoppers in a mall have a mean weight of 70 kilograms with a standard deviation of 10 kilograms. An elevator at the mall holds a maximum of 6 people, and safety engineers are curious about the average weight of shoppers on a full elevator. Suppose that we take random samples of 6 shoppers. So that's kind of what we're doing. We're supposing that we take random samples of 6 shoppers. We're assuming that like any elevator is kind of like a little random sample of 6 people if it's a full elevator. And we're going to calculate the mean weights of these shoppers in each sample. So what we're doing is we're imagining that from the whole population of people at a mall, we're taking 6 people at a time. So if we do that, if we take a group of 6 people, and if we keep calculating their average weights, so if you take 6 people, they'll have one average. You take another 6, they'll have another average. Eventually, they'll start to form a bell curve. It's going to look like the one in blue because we're measuring an average. We're measuring a weight. So we're expecting a center of 70 kilograms. So the mean of our sampling distribution, if I were to draw what all the samples would look like when n equals 6 with a sample size of 6, I would expect them to be a bell curve where the center is 70. So that's going to be the first answer here. The center of the sampling distribution is 70 kilograms. And the standard deviation of the sampling distribution, it depends on the sample size. So here, the formula is in blue. So our standard error is the standard deviation within the population, which is 10, divided by the square root of the sample size, which is 6. So the standard deviation of our samples is going to be 10 divided by the square root of 6. Let me do that. Let me try to do that here for you. 10 divided by square root of 6. 4.08, we'll round it to 4.1. Because it says to round it to 1 decimal place, I think it'll take 4.1. All right, very nice. Flavia was curious if a sample first quartile was an unbiased estimator of the population first quartile. She started with a large, normally distributed population of test scores whose first quartile was 70. She then took random samples of 6 tests and calculated the first quartile of each sample. She replaced those tests and then repeated the process for 50 trials. Her results are summarized below. So what you see here is a dot plot. It's a graph of all the samples of 6 tests that she took. And what she did is she took 6 tests again and again and again, and she calculated what was the first quartile of those tests. She was looking for the number 70. 70 is what we're expecting. 70 would be reasonable because that's the first quartile of the population. That number appears to be here, 70. So now the question is, what do we think? Do all these samples do a good job of estimating the number 70? To me, although it is pretty spread, it centers at 70, and it kind of looks like these bell curves we were talking about. This actually, I think, does a pretty good job of estimating the number 70. It peaks at 70 for one. It's kind of peaking towards this middle here. There's a lot in the middle, and then it's kind of balanced on both sides. So I think I like this. I think this is a pretty good estimator of the population first quartile because we were looking for the number 70. Our samples are telling us that it's screaming 70, basically, if you look at the results of these samples. So I think it's pretty good. That C is unbiased estimator, and I will erase that. So A is saying it's biased because you're underestimating, so you're consistently getting too low. B is saying biased because you're overestimating, consistently getting too high, but that's not happening. We're getting what we'd hope to get, kind of a distribution that's centered at the right number. So I think C, it's an unbiased estimator. It's a good way to estimate. Question says, Dr. Lopez gives students 90 minutes to complete the final exam for her course. Most students use almost all the time allowed, and relatively few students finish early. So the distribution of times that it takes students to finish the exam is skewed to the left. Okay. The mean and standard deviation of the finishing times are 85 and 10 minutes respectively. Suppose we took random samples of 40 students and calculated X bar as the sample mean finishing time. We can assume the students in each sample are independent. That's great. What should be the shape of the sampling distribution of X bar? So what we're doing is all these students take some amount of time to take the test. They have 90 minutes max. So you're going to get a distribution where, like, if you plot the times and this is 90, it's not going to go above that. And I think like 85 will be pretty popular. The average is 85, 80. But what's going to happen is if you like keep doing it, like some people will finish faster. So like I want to make sure the scale is good. So 90 to 80 to 70 to 60, like this is 60. So what's going to happen is a lot of people will take the whole time. The average is 85, so like a huge distribution, but you might get like some small amount of people that are finishing at 60. So this is the skew left that they're talking about. So what we're going to do is we're going to randomly take 40 students at a time and calculate their average. The question is, what would be the shape of the sampling distribution? So if we're taking samples from the skewed population, well, the central limit theorem is kind of like what these question sets are talking about. It has to do with the concept of a normal sampling distribution. So look at these over here. There's a reason I drew these bell curves. As long as you're taking big enough samples, your samples will start to form a bell curve around the true answer, as long as you're taking big enough samples. So basically, I'm going to want to say that it's going to be a normal sampling distribution as long as the sample size is big enough, and the sample size here is 40. Typically, we are looking for a sample size of 30 plus. That's the rule that Kahn uses, so n needs to be greater than or equal to 30. So because of that 30 number, it's going to be big enough to assume a normal sampling distribution. If we're talking percentages, they're going to talk about 10 successes and failures. I'm not going to write that because in this case, like that's not what we're not able to measure success or failure. You're just taking an average amount of time. You need a sample size of 30 plus. We have 40, so we're going to say it's a normal distribution. If the sample size were 20, for example, you would say skewed to the left, because the sampling distribution is not going to be normal if your samples are not big enough. Hopefully that helps. Yeah, read the hints, use YouTube, all that fun stuff. So, and comment if you have questions. A scientist studying water quality measures the lead level in parts per billion at each of the 49 randomly chosen locations along a water line. Suppose that the lead levels across all the locations in this line are strongly skewed to the right, with a mean of 17 and a standard deviation of 14 which is parts per billion. Parts per billion. So mean of 17, standard deviation of 14. Assume the measurements in the sample are independent. What is the probability that the mean lead level from the sample of 49 measurements of X bar is less than 15 So what we're doing is we're taking samples of 49. We're measuring a mean. So we're going to use these formulas, this concept. We would expect our samples to follow a normal distribution. The center of the sampling distribution should be 17, because that is the true average within the population, 17 parts per billion. The sample size is 49. This will dictate the width of our sampling distribution. Bigger sample, smaller deviation. What is the deviation for us? It is specifically using this formula. I won't circle that. It's this formula. I'm going to have to erase these arrows at some point. So the standard deviation of the population is the numerator. So it tells you that that is 14. So the standard deviation, the standard error for our sampling distribution is 14 divided by the square root of the sample size. The sample size is 49. So this is 14 over 7, which is 2. So what does this mean? When we take samples of 49, we will not always get 17. We will get a distribution of results. We'll get somewhere in this bell curve. We'll get a result somewhere in the bell curve. 68% of the time in a normal distribution. So if you've studied normal distributions, 68% of the time, you're going to get a number plus or minus 1 standard deviation. So here the standard deviation is 2. So 68% of the time, you'll get averages between 19 and 15, because that is 2 away from the mean. Now it's asking, what is the probability that you get less than 15? So that works out kind of well. So if we know that in a normal distribution, 68% of the distribution is plus or minus 1 standard deviation, if this is 68%, that means there's a remaining 32% that is split evenly on the left and right. So that would be 16 and 16. So this part of the curve here is 16%, and that is the answer to the question. Because if you look at this, this is 15 parts per billion. It is 1 standard deviation below the mean. What is the probability of getting something less than 1 standard deviation below the mean? That is 16%, and I'm using the empirical rule here, where 68% is plus or minus 1 standard deviation. So let's check it out. Answer of 16 looks very nice.